record. And we are now recording. There we go. Thank you. Excellent. Everybody should be able to see my screen, yes?
Yep.
I'm going to go ahead and get started.
Yeah, Doug, I booked it for an hour. I forgot that the last one was an hour and a half, but I don't know if we need more than an hour.
It's probably about an hour. Yeah.
Okay.
Yeah. It depends on how many questions there are.
Okay.
All right. So let's get rolling here. So we are on part 2 of the basic data primer, and really this is the just quickly go over the agenda. We're looking at part 2, which is the actual talking part, the communication part, the chatty bit, what I like to call it, and we're going to touch on some troubleshooting tips and tricks near the end of the presentation as well. So first off, we're going to start with that talky part, and talk about physical devices. The physical devices that we typically will encounter, and it depends on, you'll notice that the L level, okay, the L1, L2, L3, that refers to the OSI model, and where these pieces of hardware actually exist in that OSI model. I don't want to reiterate the training from last time, but the OSI model is like that packaging, encapsulation, and de-encapsulation of information. Like putting an envelope, putting a letter in an envelope, putting that envelope in a mailbox, putting that mailbox in the back of a truck, and transporting it to the other end. That's essentially what the OSI model dictates or describes in its purpose. So equipment that we typically will see, devices, will have things like repeaters, excuse me, and repeaters, it's essentially our regeneration device. So we're going to have things like media converters and Ethernet adapters, or Ethernet access point duplicators or repeaters, things like that, that allow us to stretch a distance or push a distance farther for a given media, whether it's wireless or wired connection. Things like modems, everybody's familiar with DSL and DOCSIS. DOCSIS is the standard used in cable modems, and it's data over cable is what it stands for. And of course, Ethernet rides on top of both of those, being a layer 1 device. A hub is a pure layer 1 device, and it's, don't be confused with a switch. When somebody says they have a hub is a layer 1 device. Okay, so it's a half duplex typically, and forced at 10 meg. You're going to want to stay away from hubs completely. You always want to kind of do all of your consolidation or amalgamation of connections through a switch, and that switch is going to be that layer 2 device working at the MAC layer, and we're going to talk a little bit more about that in the next coming slides. The intelligence of where information is going, of course, is going to be run by the router. That's the layer 3 device, and you typically, the green and the purple, or sorry, the green and the blue, which is layer 2 and layer 3, are the 2 areas that we primarily talk about in data networking. And you'll say, okay, what's your layer 2 network like? And we're talking about switches and your physical network, your physical connection, your aggregation points, that type of thing. And then, what does your layer 3 network look like? What's your logical routing? Default gateway, where does your packets transport? And where do those decisions made? Which is your router. And then finally, up above that is your hardware and your software that runs inside that router, and that's your hardware and software from layer 4 to layer 6, and of course the application itself, which is up at layer 7. Now, all of that information, of course, it really emulates the whole envelope and letters and the mail, the postal system, because of encapsulation. And really, if you understand encapsulation, you understand the OSI model much better, and you can understand what's happening in the data world. Yes, it's still hard to diagnose, because you have to get down and start unpeeling the onion, and peeling away layers and layers of encapsulation to get to different areas. And that's where things like sniffers and packet analyzers come into play, where you can actually look at this data inside. Really, what we typically look at is the encapsulation of TCP and IP buried inside that, or the IP information with TCP buried inside it, and that's where we realm. That's where we work typically 99% of the time, and that information really captures, the destination. Where is that packet going to? Where is it coming from? Whether it's the source or the destination, it's very, very important information to have. Now, when it comes to kind of translating that, okay, what machine is talking that information? We talked about an ARP table, and address resolution protocol is kind of the next point where ARP comes into play, and that IP address does translate to a MAC address on every network. It has to, or packets just aren't going to get where they're supposed to go. A physical device, a physical piece of hardware, and that includes phones, routers, switches, anything that is going to talk in a data world is going to have a MAC address, and that access layer is very very unique, because the addresses that you have there are broken down into two segments with a MAC address. Part of it's the manufacturer of the hardware, and part of it's the ID of that device. Technically, every device in the world that has the capability of communicating in a data stream is supposed to have a unique MAC address. Okay, I have actually physically run into devices with the same MAC address. It doesn't happen very often, but it certainly does happen. But at a logical level, they're supposed to be unique. Typically, you're going to have no duplication inside a customer network at any point with the manufacturer's hardware, Polycom, Cisco, any firewall equipment with MAC addresses that are tied to those IP or physical devices. You're not going to run into it, because they're typically enterprise grade gear anyways. So we have that IP address, and you need that MAC address, and that's kind of touches a little bit into the into the troubleshooting, where you can actually use a command prompt on a Windows machine, anyways, which is the ARP command, and right at the C prompt, ARP-A, and shows the content of that ARP table on that PC. So if you do a ping to a given piece of hardware, and you do that ARP-A, it will actually show you the MAC address, and you can verify. You look on the bottom of an iPad or a smartphone, or you're in the inside of a smartphone, that is, or in the bottom of a Polycom phone, or in the back of a router. They'll always have a stamp or a label that says this is the MAC address, the physical layer address of this device. You can compare that number to the ARP table, and suddenly you know the IP address. You get on your computer, and you can now ping that device to see if it's awake, or you can go into the HTTPS or HTTP on a web browser and go into the management portal for that physical device, if it has it turned on, of course. Sometimes problems with routing, and this again is a little bit of a troubleshooting tip, is to clear the cache or to clear that ARP table. ARP-D is that command, and I don't tell people not to use it. It does take a little bit of time to relearn that MAC table, but really it's transparent to the end user. We think of things happening in real time. They actually run really slowly for humans. Computers are doing things at light speed or near light speed, so it looks like it's instantaneous to them, whereas we're very impatient, and obviously we're running a lot slower. Now, when we talk about the MAC address itself, the MAC address resides, and I kind of touched on this already, on the NIC card. Oh, hang on a second, I gotta mute somebody. Can you mute Tanvir? We get a lot of background. Hey, Paul. There we go. Perfect. Thank you. Yeah, so the NIC, or the network address card, that's built into a piece of hardware, has that address burned into it. And yes, it's a layer 2 address. Media access control is what MAC stands for, used by Ethernet. It's kind of standard around the world. The IP address types that we typically will talk about, and different types of IP addresses, are things like unicast, multicast, broadcast, and anycast. In our world, 99% of what we communicate is all unicast. It's all one-to-one. Multicast, we don't actually have any services on the Ring Central or on the Business Connect side that utilize multicast. There are some PBXs and VoIP machines out there that use multicast for paging, for example. They'll page multiple devices or multiple phones at one time using a multicast protocol. We don't do that. Everything is considered a unicast, and that's kind of one of the restrictions why we only can do 10 devices at a time, is to limit that unicast traffic a little bit. Now, other address types or casting type is broadcast, and broadcast is used almost all the time, and that's things for DNS discovery or DHCP discovery is all done to broadcast, and that's typically it's going to be the broadcast address of the IPv4 address, which is typically it's the highest IP address in a scope or in a range of IP addresses, what we call a subnet. And then finally, Anycast. There's kind of a couple of versions. IPv6 uses Anycast, and also there's also BGP, which gets into a different realm. But BGP has Anycast as well, that can route traffic to the nearest location depending on what the IP address is based on. And we don't really touch on that. But for the most part, what you're going to see is unicast 99% of the time, and 1% of the time it's broadcast. Everything else is used by other applications in our world, anyways, in voice over IP. The IPv4 address, we're talking 18 million plus private addresses or private networks that are available because of that 2 to the power of 32, because it's a 32-bit address, and the bits can bounce from 1 to 0 or 0 to 1, giving you that that quantity. Now, because of what we call CIDR blocks or classes, typically it was classes when IPv4 was first imagined, and then we subnetted or super subnetted IP addresses into smaller and smaller blocks. It became a CIDR, which is classless interdomain routing, is what that stands for, and the IP address range really dictates the number of masked bits that IPv4 or the IP address actually works in. So you can separate network from hosts or devices, and Class A network was a 255.0.0.0, 10.0.0.0 would be address, for example. The net mask, the first portion or the first subnet, the first octet of that address would designate the network, and the rest of it are hosts. So 128 networks for Class A and 16.7 million hosts for that network. And then you kind of break it down further into a Class B. You've got the 172.20, 172.16, typically a Class B network, where you've got 16,384 possible networks. On the left-hand side of the net mask. On the right-hand side of the net mask, the .0.0 are your hosts, 65,000. And then, of course, most commonly, we're going to see things like Class C networks, and that's that 255.255.255.0, being the first 3 octets of 255 is your network side of it. And the .0, which is 8 bits, it gives you 254 possible combinations for hosts. And I love the counter on the right hand side of the screen there. The digit 4 is my favorite. When you see it count up to 4, there it is. It's kind of a funky thing. But yeah, I taught my son how to count in binary using his hand, and he was like blown away. He says like, "Oh my God, I can count like a machine." And I said, "Yeah, you can, and it's just a matter of turning digits 1 and 0 on and off. That's all it takes." Now, talking about the CIDR blocks and the subnets, and what typically you'll see is a /24, which is a full Class C. That Class C can then be broken down into smaller and smaller subnets to give you the ability to route between networks, and that gives you the ability to set up a given gateway or a smaller network that can communicate through a router to make a routing decision between 2 networks. And as I don't know if everybody's heard this, but I've mentioned it many times that you know, the internet is basically just a network of networks, and internet access requires an IP address to the outside world, and we'll talk about NATing in a little bit of time, network address translation. But every device has to have an IP address to identify themselves. I like to call them telephone numbers too. You got to have a unique telephone number to be able to communicate point to point. And with a subnet in an IPv4 address, you have to have at least one IP used for the network and one used for the broadcast. So the usable IPs are always -2 from the total available out of that. Now, I'm not going to go into you know, into great detail on how to break down these subnets, but the next couple of slides will kind of explain it a little bit. What we're essentially doing is masking ones and zeros in a subnet mask to say what part is host and what part is a network. This is where you see that. So on the left-hand side, that's not covered in a box are the networks, and on the right-hand side, where the red boxes are, for those different class of addresses, you have the hosts that are available to use those addresses. And it's just a combination of ones and zeros to get your IP address. And you'll notice the counter at the bottom is counting up and using those ones and zeros to give you a higher and higher number. 8 bits, you've got 256 possible numbers to play with to play with that. And the really cool thing is that every machine has to have an IP address, as we've kind of discussed already. But there's some default IP addresses that every machine has. One is a loopback address or a home address, which is a 127.0.0.1, and you know, that always refers to its own device. Anybody can ping 127.0.0.1, and you will always get a response. If you don't, you've done something severely wrong, because that means the network card is not even looking at itself, because basically you're pinging yourself. And I saw a T-shirt at a convention one time, and I just loved it. And it was this one. There's no place like 127.0.0.1. So yeah, there's no place like home, and that's really what that IP address does. Now, when it comes to communicating, of course, you need more than just an IP address, and you need a port range or a port number to designate whether it's an individual conversation that you want to have point to point. Now, I'm talking machine to machine, that is, or it's a particular service that you're looking for. And those port numbers that are used in conjunction with the IP address really start to tell it where where that information is designated for, or what it's being used for. Port 80, for example, is HTTP. 443 is HTTPS or secure HTTP, things like that. And you know, it goes on and on. Those are all those well-known ports from 0 to 1023. You know, we have registered ports. Anybody can use them for any purpose. It's not nailed down. It's not a legal requirement. It's a best practice, and the IEEE or INAN has designated those port numbers to be used for certain aspects. A lot of this information was very, very old when it was first. It's been around for a long time, and a lot of the services are kind of cross-functional, so they can use it for a lot of different things throughout the range of communication. Now, you're probably wondering how all this stuff gets assigned and who does what and that type of thing. The IP addresses that do get assigned, or assigning IP addresses, typically it's a service called DHCP, the Dynamic Host Control Protocol. And DHCP is something that our devices will use on a regular basis. And it's to get the IP address, because everything uses dynamic IPs, because we don't want to have duplicates on the network. The second you have a duplicate IP address on the network, the communication to both devices stop. because you can't designate information to two devices at the same time with a unicast IP. It's like, you know, two people talking to one person, you know, or having a webinar and having somebody leave their microphone on. Nobody can understand because there's just jammed up with data. Paul knows what that's exactly like from our meeting this morning. So that's kind of the need for dynamic IP addresses. Now, the IP itself is a mapping of that host name to an IP address, which is your MAC address, and it will do lookups, you know, through the internet or locally through a domain name system or DNS. I like to quickly call it the phone book on the internet. So I need to get a hold of cbc.ca. What IP address is it? Okay, and DNS does that for me. I need to get a hold of ringcentral.com. DNS does that for me. I need to provision a phone, which is pp.ringcentral.com/pp. What IP address is it? The DNS system does that for me. Okay, whether it's cached or it's a fresh lookup, it all works essentially the same way through the internet and through your local network. DHCP. Talking about the assigning those IP addresses, it's all done dynamically. It's all done on demand, and the handoff back and forth between DHCP and a device is a multi-handoff or a multi-handshake offering. And it basically says, hey, you know, I'm looking for a DHCP server. Can you give me an IP address? And DHCP server says, hey, yeah, I can offer you this one. Would you want it? And you say, yeah, okay, I'll take that one. Okay, and then you're assigned. And that's how the DHCP protocol basically goes back and forth and says, okay, you need an IP address, I'll give you one, and assigns it and then keeps track of it. The other way, the opposite of DHCP is a static IP. Typically, we try to stay away from static IPs because it restricts a lot of things when it goes to growth. You know, you have the possibility of devices having the same IP addresses as well. Where you're going to see the static being used a lot more is in a server environment where you know, you have to have a device on the same IP address all the time. DHCP gives you the ability to do that anyways through reservation, address reservation, and I got one device. Somebody's got two microphones running at the same time here. Okay, it's quieting down. That's better. So yeah, the servers are typically going to have a static IP address being used, where they're going to have the same IP, same mapping, same NAT statements pointing, say, outside traffic, web traffic, an FTP server, a mail server, HTTP or a web, you know, whatever server it has will have a static assignment, so that address never changes by a DHCP, for example. Now, trying to communicate to any of these devices, the first thing you're going to try to do is just check connectivity. Ping is not a test for quality or anything of the sort. ICMP is the protocol that Ping uses, and it's simply a connectivity check to say, hey, can I talk to you? Yes, you can. Okay, how good that connection is, that's not what Ping's used for. It's not a quality check whatsoever. So when you look at a ping and you get different different ratings or different response times, you know, that response time is really dependent on a whole bunch of things. You know, for one instance, if you do a ping to 127.0.0.1, yeah, it's going to be less than 1 millisecond because you're pinging yourself. Okay, it's not even going out the interface. It's just looping right back. You know, and you ping other devices, for example, like pinging 8.8.8.8. Anybody know what that is? Yes, it's the Google DNS server, you know, that might take 17 milliseconds. If it's busy, it might take 117 milliseconds, but typically it's going to be you know, fairly low. You know, you ping something like 4.2.2.1, you know, that's going to be another DNS server out on the internet, and it might be residing in a different state or potentially a different country with a higher ping, that has 36 milliseconds of round trip time. Typically, it's going to be in the East Coast from the West Coast. And it's really just to check to see if something is alive, something that it is responding, and that's all it's used for. You can do things like, you know, pinging using a name. It will do a lookup. So you're doing two functions. You're doing a DNS lookup. At the same time, you're doing a ping to that far end device to say, hey, are you alive? So you're doing kind of two checks. If you do ping www.isc.org, the first thing it has to do is to do a DNS lookup to say, hey, what IP address is that? And then start pinging to that IP address and then responding back. So yeah, I sent 4, received 4, I lost none, which is good. Okay, but that response time is around that 38 millisecond average, 36 millisecond average, which is a pretty decent connection. And you know, you can do that in any realm. It makes it very easy to check your DNS servers too, just by doing ping and a name, whatever it might be, any name. DNS will activate and try to resolve, do a forward lookup for that IP address, which is a quick little test of DNS to make sure your DNS is set up correctly too. Now, name resolution itself is used. Let's see now. When I can't remember why I put this slide in here, to tell you the truth. Yeah, too many host names. Yeah, we need a dynamic automatic solution. Correct. Solution DNS is distributed, hierarchical, and database. Okay, yeah, that's name resolution. That's forward lookups. DNS is used for, if I remember correctly, DNS is used to resolve IP addresses or names to IP addresses, and it does validation of that name to give a single IP address. Okay, and yes, it is the Internet's phone book. It does that conversion from name to number. And you can also use reverse DNS. Mail servers will always use reverse DNS, or they should, to validate whether the IP address that it's coming from is in fact the name of the domain that the email service is listed by or listed from. So if you say, you know, jimsmith@mail.com, and I send an email off to a user, and it does a reverse DNS lookup to say, hey, what name is this IP address? And the IP address comes back as google.com. It will typically kick that out or block it to say, okay, it doesn't equal mail.com, so there's a reverse DNS mismatch, and it will block that from considering it potential spam. Okay, and yes, DNS is globally distributed in a hierarchical database that continually updates itself. It's based on a really old protocol called Bind, and you can look that up. Just to Google search on Bind and read to your heart content. You can get buried in all old documentation on that stuff. The domain name system itself breaks down a lot of the names that we get, starting from the top level domains or TLDs. What we typically will see is things like country codes, you know, .ca, .uk, things like that, or generic top level domains like .com or .ca. They're all considered top level domains, and that search is done quite extensively. There's a whole mapping system of how the root database is built out. First, it looks at the first letter of that root domain and then points it towards a server and says, okay, anything that starts with C, .c, we'll look up .ca or .com for .com or .ca, and then it goes from there, and then builds out and builds out farther and farther and farther until you get an actual IP address. A little more detail on DHCP, assigning the addresses to host. A lot of the stuff that a device needs to communicate, it requires an IP address. Yes, absolutely, it requires a subnet mask to know, you know, what is inside its own network, because a subnet mask is another version of, hey, I am part of this network. Therefore, anything I'm looking for, if it's an IP address that's not on my network, I have to go out through, guess what, my default gateway, okay, towards my router. My router will decide how to get there and how to get back. And it will also give me my IP addresses of my DNS servers. So those 4 things are the most important thing that you'll see from a DHCP server that will come back from it. That is the minimum requirement to make a data call or a data connection. The IP addresses and networking and all the stuff we're talking about requires the address, which is the class A, B, C, D, whatever it might be, or fixed classical addressing, and it breaks down the network, or divides that network into subnets, and what we call super subnetting, or CIDR blocks. Classless interdomain routing allows you to aggregate or add addresses together to say, okay, I'm part of a bigger network, and gives you the ability to have an aggregation point. Instead of having a list of thousands and thousands and thousands of networks, you can subnet or super subnet those addresses into a bigger block to aggregate them, to say, okay, I need to go to 10.4. Well, 10.'s not a good example because it's a local address, but 205.16.4, okay, may include .5, .6, .7 in that third octet, that would be included. So you'd have a larger address that would aggregate those networks together to make a routing statement or a route table smaller in size, because the route table is very huge on the internet itself. With VLSM, which is the variable length subnet masking, that's where we can break out unequal or different size networks where a requirement we need 5 addresses, we need 13 addresses. You can use that VLSM, which is the slash, anything smaller than a /24, /25, /26, 27, 28. Yes, it's a bigger number, but it's a smaller network, or a smaller number of hosts on that network. Okay. In a routing environment, a hop or handoff point, it's not actually a hop, a jump from point to point. It's actually a handoff point is what hop stands for. And you say, okay, how many hops are in this picture? Really, there's 3. And that data has to get from each point to each point. When you do a ping or a trace route, you'll see this in a trace route. When you do a ping, you'll only see that one connection from the first network on the left, 128.1 to 128.4 on the right-hand side. You won't see any devices in between. If you do a trace route or trace RT, you will see all of the devices in between that will give you a better picture of what it's communicating and how much difficulty a route is taking to get to a certain location. Excuse me. Now, UDP, or User Datagram Protocol, what we like to call connectionless. Actually, the internet calls it connectionless because all of the information that's passed in a timely fashion is going to be UDP. So real-time protocols, RTP, are going to be a connectionless. It's I like to call it send and pray, or fire and forget, are the two terms. There is no error correction on UDP. There is no handoff to say, hey, have you got it? And there's absolutely no tracking of that data. It is simply send the data as fast as you can to a destination, and you hope it gets there. And that's why voice communication is important to run on UDP, so it gets there faster than TCP, and it's very simple, very efficient. But if there's data loss or packet loss, we lose conversation. We lose parts of conversations for that data that passes point to point. Now, when we have a signaling characteristic that we cannot lose data for, we use TCP, and TCP has a whole a handshaking back and forth, SYN, SYNAC, and ACK, that will set up a connection to say, hey, are you there? Yes, I'm here. Okay, I'm going to send you data. Are you ready? And it sends that data. So that handshake then will go out from a certain piece of hardware to say, hey, are you ready to send it? Yes, I'm ready to send it. Okay, have you received this? Yes, I received it. Okay, I'll send you another piece. Did you get it? Yes, I got it. Okay, I'll send you another piece. And it goes on and on and on. You can imagine the amount of overhead this creates when you have that data transfer and you're getting those acknowledgments of each individual packet. If you don't get a packet, guess what? It retransmits, so it can correct on a packet loss error. In in the voice over IP world, when you put voice over IP over top of a network that seemingly or maybe mysteriously has never had an issue, because all they did was surf the web or email or file transfer, and then suddenly they're putting voice over IP on top of that network, and they suddenly find out that their voice network really sucks. It's bad, it's poor connection. Typically, it's because of light packet loss or moderate packet loss. TCP can recover from that, and you don't typically see any degradation in service, other than it looks a little slower than maybe at home or from another office. TCP will recover from data loss. UDP, when you put it on top of it, that voice connection will lose the data. It loses it, and it's gone. It's gone forever. So you lose that that syllable or that sentence or part of that conversation. It just won't be there. So that's why it's important to have a strong network, and network is paramount. So you've got to have a clean network that doesn't have packet loss to achieve good results. Now, getting packets from point to point requires routing, and there's different types of routing. There's tons of it. I won't go into great detail. This is a course all on its own to talk about routing and dynamic routing and routing protocols and things like that. But essentially, it's a routing point that says, hey, what are my neighbors, and where do I send data that I don't know where it goes? If I don't have a direct connection, a router says, okay, I don't have a direct connection to that network, so I'm going to send it to a default gateway, and hopefully the next guy knows where that data is, okay, or where that endpoint is. And it continues going through the internet until it finds where that route is. Now, that kind of harkens back to our subnet and super subnetting slide a couple slides ago, where we have aggregation points to say, okay, for this routing endpoint, this address that we're looking for, it exists on my next hop. So I can go to that next hop, and that next hop says, oh yeah, I have a location for that, or I have a route for that, a port that's connected to a different network. Send that traffic my way, okay, or out this door to the next device. And we have things like direct routing, indirect routing, static routing, dynamic routing, and of course convergence when things happen on the network and routes fail or connections fail, and we have to rebuild that. It does take time for convergence to happen. I don't know if anybody has experienced it on the internet. If a major point fails, you'll suddenly lose. You'll lose performance. You won't lose connectivity. You might lose a little bit of connectivity, but you'll lose performance. It'll look like everything's starting to lag and slowing down. It typically means that a route to the endpoint has failed, or a physical piece of hardware, or it's a transmission medium has dropped off the map, and a new route has to be discovered, which is and those route tables have to be built and then communicated through all the network to say, hey, I have a new route for this, and that's convergence to basically get that information at the far end. Like I said, this could be a course all on its own. I don't know if anybody's interested in it, but it can be quite extensive. Now, routers versus switching, it's important to understand that the difference is routing is connecting different networks together, and it's basically just authorizing whether an IP address or an endpoint can talk to another endpoint and has a route for it. Whereas switches extend networks, and they forward packets based on a couple of things: MAC addresses and VLAN IDs, and typically they will fire them out as fast as it possibly can. Forwarding and filtering on switches typically does it at what they call wire speed, and backplane speed is important on a switch. When you're purchasing switches, you need a very fast backplane. Typically it's gigabit or higher nowadays. Typically they're 10 gig or 40 gig or even 100 gig backplanes, and that's the speed at which, or the bandwidth that's available for a port-to-port communication to an end device. Now, switching versus routing, the rule is route once, switch many. and that's a really good rule to live by. You want to route as little as possible, but you can switch as many times as you want. Simply because switch is done at near light speed, and routing requires a calculation or an analysis of where that packet comes from and where it goes to, and a rule or a table has to be kept to figure out where that comes and goes, okay, inside it. And yes, switching is easier to configure. It can be a bear if you've got layer 2 failover protocols, things like spanning tree and things like that. It can drive you nuts because you have spanning tree failures with root ports and non-root ports, and having networks kind of flap up and down because of a bad port or a bad cable. Somebody ran their chair over a Cat5 cable in a computer room while they were changing a server, and suddenly the network is slowing down because of a bad cable, because of a flapping port. That's a port that says, hey, I'm available. No, I'm not. Hey, I'm available. No, I'm not. Hey, I'm available. And it just keeps doing that up and down, up and down, up and down. Not a good thing. But switching is definitely faster than routing. So what we say is live by that rule. Route once, switch many. So we have a Q&A. Mics are open. If there's any questions, pop them up now, because we're going to drop into troubleshooting next. Must be old hat to everybody. That's fantastic. Okay, and I know we're not muted as a whole. So if anybody does have any questions, just either throw them up on chat, or we can ask them at the end as well. We're almost there. We're less than 10 slides left, so we're actually moving along quite well here. Okay, let's touch on troubleshooting and looking at the elusive, kind of invisible magic behind the curtain when it comes to data networking and how difficult it can be to troubleshoot. So, kind of the common steps that we typically look at is identifying the exact issue. So you want to make sure that you understand exactly what's happening. And what the symptoms are. The first thing to do after that is to try to recreate it. See if you can recreate the problem. And if you can't recreate the problem, maybe you're not hitting the right problem, or you're not using the right gear. And then, of course, I think the most important part of it is breaking down that connection and isolate. Start at one end and break down, segment your troubleshooting. And that means connectivity tests. We'll talk about that in a second. And making sure that we have link lights, the layer 2 link lights that we're communicating, and making sure that we can ping from point to point, and then we check for the quality of that connection, and we do that per link inside the network to kind of isolate that breakdown of communication. So that's very important. Step number 3, isolating the cause, I think is the most important thing. Then we try to formulate and implement a corrective action plan, and say, okay, if we're going to change this is the result that we should see, and then implement that. If you do see exactly what you planned, then you're doing the right thing. And you're seeing that improvement. If it doesn't, then obviously you go back a couple of steps, and maybe you recreated the problem incorrectly, or you isolated the wrong portion of the network when you're troubleshooting. And then, of course, when you get the solution, you test it and make sure that you can stress it to make sure that it doesn't fail, or that it's actually working correctly. And most importantly, document what was done, or document the solution, document the network to see what the next person that comes in, when they go to look at it, they'll know exactly what what has been done, how things have changed, what changes you've made. Or what changes are required to eliminate the problem or eliminate the issue, because it might be out of your control too. It might be part of somebody else's network. But documenting that is really, really important, and just slowly follow through the steps and document each step. Even a quick notepad, writing down what you're doing. to make sure that you can communicate to somebody, when you're talking to an ISP and say, I've done this testing and I've done these steps and I've broken down the network and I can see the problem in your network, or I think the issue might be in the ISP, without a clear, concise document to kind of identify that. Most people will say, well, I don't follow you. I don't understand what you're talking about. And you'll run into that all the time. So the first thing to start playing with is ICMP. And ICMP, Internet, and great. I think PowerPoint has just crashed on me because my other screen is saying PowerPoint is restarting. Yes, it is. Nice. Look at that, Microsoft, quality products. Okay, and we're way on the wrong side here, not on the slide. 74, I think we're up to 60 something. Yes, there we are. Okay. So ICMP, Internet Control Message Protocol, or PING. PING and traceroute use ICMP specifically, and that's the hey, are you there? Hey, are you there? Hey, are you there? And the response back is, yeah, I'm here. Yeah, I'm here. Yeah, I'm here. And a couple of measurements are taken. One is the amount of milliseconds it takes to go from end to end, and the other thing is, did I get all of it, which is your packet loss. And okay, Brandon, are you having an issue? I can't stop staring at that GIF while I'm trying to listen. Nice. Okay, I guess that was an old message that popped up.
Little late on that one, Doug.
Yeah, no kidding, no kidding. I just saw it pop up. That was kind of weird. That's okay. Okay, so I guess that was my number 4, right? The favorite number 4 there, Brandon?
I'll have to go back and look at it.
Yeah, I think it was. Okay, so let's talk about ping. Not a lot of talk about ping. Like I say, there's a couple of components that make up ping and traceroute. One is the amount of time it takes for that message to get point to point, that return time, and the second part is did it all arrive? Your packet loss. So there's a couple of things that you can do inside the ping command itself, and I think did I miss a slide here? No, I didn't. There we go. And the first thing I like to do is run an IP config to make sure that the device that I'm calling from, I know the IP address of it, and you've got the ARP-A to look at your ARP table to see, okay, what devices am I connected to, and which ones do I know that I have a route to, because I know the MAC address of that device. Netstat with a -A or -B or -R give you different results, but Netstat is a phenomenal tool to see what's actually running on your laptop or Mac that can tell you what is happening. I think Netstat is actually a command that's a Windows-based command prompt. Traceroute, TraceRT will send pings, and pings are what we've talked about before, that allow for that traceroute to actually capture each one of those hops. We'll see the traceroute here in a second, and it, like I say, it does use ping to get to each point. So when it does a traceroute, it'll say, hey, for each hop, I'm going to do an individual ping and report back. The next hop, I'm going to do another ping and report back, and so on until it gets to the end point, is what the traceroute does. So that's a really good indication of a couple of things. One is if there's an issue with the number of hops, like why is it taking so long to get this connection through, you can see, oh wow, it's 45 hops instead of 14 hops or 2 hops. And also it's supposed to be a direct connect between TELUS and Ring Central, and it looks like we're going through a third party. So there's obviously a route that has dropped, and it's an alternate connection that's getting there, and it's going through that third party. You can see that inside the trace because it'll show you the ISPs that are involved in each one of those hops. Now, in that traceroute command, when you run it, it will show your response times to each one of those routes. I did a quick route to www.bell.ca to see where it was going, and what you typically will see is a gateway from where you're starting through the network. And you'll notice I see Quest, which is a U.S. carrier, into the Chicago data center at hop number 6, which happens to be owned by Bell. And then Bell's network carries that traffic through Toronto at hop 8. And everywhere you see request timeout, typically what that means is that the router that is supporting that connection is not replying to ICMP because of either performance requirements. It needs to downgrade, or it ignores ICMP completely. And you can turn that off even on a home router. There's an option that says ICMP, respond to ICMP package, yes or no, and you can turn that on or off on your home router. Coming up the last couple of slides here, Q&A. Okay, let's open it up again. Now I've only got this and a thank you slide. We're almost done. So questions.
I'll start us off then, Doug. It's Brandon.
Yeah.
I have a customer we set up with the QoS settings for all the port triggering and everything that was recommended with their gear. And since we had gone in and done that, they've had some significant changes to their internal network, including getting a static IP for a car dealership program they required, and that involved there's a firewall in there from another company, plus there's this other router that they had to provide for their services, and we have our switch and our router in there, and their mobile additions, like 20% of their calls on the QoS reports are coming back as poor or moderate, and it's most of their sales guys. They're getting really frustrated, and I'm kind of running out of ideas as to how to troubleshoot that, because we did go in yesterday and look at the setup. We looked at, we did a trace route on it. We did a ping to see what it was, and it was doing 17 hops through all the way to Washington and back. What would be something that we would look at there in your experience with the mobile users? Now it's a regular edition, premium edition, but these are the mobile users who are using the mobile apps that are experiencing packet loss.
Okay. Are they mobile users connected to the Wi-Fi network, or are they using LTE?
Yes. Yeah, to the Wi-Fi network. To
the Wi-Fi network. Okay. So when they communicate to the Wi-Fi, are the mobile users actually using VoIP? Yes. Is VoIP turned on while on Wi-Fi?
Yep.
Okay.
The mobile app is important for them because they want to be able to transfer calls to other sales guys. And they didn't want to use the short code, the # extension #, because that was too much to remember 3 different extensions.
Okay.
And I get that. Like we should say that the service works as anticipated. But the problem is, like I said, that their joke in the showroom right now is, "Can you hear me?"
Oh yeah.
They're getting customers calling in, and I'm looking at the QoS reports, and it's showing the packet loss between the server and them. So the only thing we tried yesterday to reduce the amount of hops it was doing, and to avoid any kind of configuration issues with static IPs and things that Bell and this Fortinet company had done, was we had basically taken the device, the TP-Link, I think, that was providing their Wi-Fi, and plugging that directly into the firewall, and then enabling the port triggering rules on that with the company that provided the firewall, as well as doing the DHCP, like allowing that. So it seemed to help a little bit, but I don't think it's the solution.
Yeah. That's actually the probably one of the first steps I would have taken to collapse the network and reduce the amount of gear that's involved. The access point has to use the same route as the firewall rules are being applied to, so that wired connection to the outside world and the port triggering that you've got set up in bandwidth reservation, the Wi-Fi access points have to absolutely use the same network to grab that. If they don't, then there has to be a connection, because 17 hops to a Ring Central endpoint is unprecedented. There's something wrong with the network as far as an access point goes, from a wireless access point, unless it's being provided by somebody else. There's got to be a different ISP. Maybe we can take a look at the trace routes, if you don't mind, Brandon. We can do that at a later date, or reconvene later to take a look at the trace routes from a wireless access point end user compared to a wired endpoint, and compare those results.
Are both those?
We did a trace route on a laptop connected to that same Wi-Fi network. We didn't do one on the other side yet.
Okay.
Are both those routers hooked up to the same switch at that client's device? The router provided by the car dealership. Maybe it's not CDK out there, but they're pretty big with car dealerships. And then the customer-owned router.
That's what we looked at when we got there, because their IT company didn't agree with this software company putting it in the way that they did. So that's where we moved the wireless router away from all of that stuff and did it directly into the firewall, like into their, I forget what they call it, the box, the red box that they have there, one of the brands. But like we avoided all of the other switching and everything else to try to avoid the double NAT and any other kind of conflicts that we would run into.
Right, right.
So anytime you have two routers on that same network, it's going to be problems unless they have like a managed switch that can put in classes of service to dictate which port it goes out.
That's right. That's right. Yeah, you want to eliminate the double NAT for sure. And that's what I think is potentially is the part of the issue. But having that 17 hop route doesn't make sense. There's something wrong there to start with. So I would drop the network down to its simplest form from an access point perspective. If the access points are acting as routers as well, they've either got to get connection directly to the ISP or turn off the routing in the wireless access points and have them connect to layer 2 through to the routing engine that's on the dealership floor, okay, with the firewall connected to it.
I'm okay to take it offline afterwards too. We can touch base and try to figure something out. Take a look at their portal and their their reports.
Yeah. Look at the reports. Maybe a network diagram that would help too to kind of visualize it and see what components are where. Again, documentation, right? To document it, because it's really the only way to troubleshoot it when you bring somebody else in, so they can understand kind of your point of view.
Yeah, I mean, I could go on site and we could always do the screen share and take a look at some of the things, what I'm seeing and what. Yeah, just two things right off the top though is a network diagram and having the trace route, compare those trace routes and see where we can isolate it from there. Okie dokie.
Okay.
Thank you.
No problem. Any other questions at all? We're almost right at the top of the hour. It's almost exactly an hour. All right. Okay, so I'm going to stop recording of this session and stop.